Today we're going to simplify radicals. And I'm going to start with one that does not really need too much work on, and that is the square root of 25. Now I'm only going to be talking about positive roots today. What is the square root of 25? What number times itself equals 25? Well, that would be a 5. What about the square root of 50? Is there a whole number times itself that will equal 50? Nope, there isn't. So what I'm going to do is I'm going to make a prime factor tree here, where I'm going to find the prime factors of 50, and I'll start with 2 times 25, and 2 is prime. 25 would be 5 times 5, and both of those are prime. So I'm done with the first part. Then I'm going to put those numbers under the radical, and I'm going to put them in numerical order. So I'm going to start with the 2, then times 5, times 5. Well, I look at this, and 5 times 5 is what? 25. And so we know that the square root of 25 is 5. So I'm going to put the 5 out here. That is as far as I can simplify it. So here is the simplified answer for the square root of 50. I'm going to do one more with the prime factors before I show you another method to simplify radicals. Let's do the 90. We know 90 is 9 times 10, and 9 is 3 times 3. Those are both prime. 10 is a 2 times 5, and both of those are prime. So I'm going to put it back in the radical, 2 times 3 times 3 times 5. And you notice I have a pair of numbers. The 2 3's are going to cancel out and come out here as just 1 3. And again, if you don't believe me, do 3 times 3. What is that? 9. What's the square root of 9? 3. There you go. And then on the inside, I'm going to leave the 2 and 5, but I'm going to multiply them. And I'll get a 10, and there you go. Another way to simplify radicals is to use perfect squares. A perfect square is a number, it's a product of a number times itself. For example, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. You see my list and it would go on forever. So when I have something like this, the square root of 20, when you think about what numbers multiply to get to 20, can you think of a perfect square? Well, hopefully you thought 4. And so my tree is going to do this. I'm going to have a 4 here. 4 times what is 20? That is a 5. And then I'm going to do the square root of both, just like this. Well, what is the square root of 4? 2. And here you go. 2 square root of 5 is the simplified version of the square root of 20. Let's do that one more time. This time I'm going to do 45. What perfect square can divide into 45? Well, hopefully you saw the 9. And so 9 times 5, square root of 9, square root of 5. What is the square root of 9? 3. Again, we don't have a square root of 5. That is a whole number, so we are done. I think I'll do one more just to show you one little weird thing that could happen. Here's the square root of 72. And when you're thinking about perfect squares that could divide evenly into 72, a lot of us know this, 9 times 8. There we go. And we know the square root of 9 is 3. And then we might say that this is 3 square root of 8, but we would not be correct. Why? Well, look at the 8. Does the 8 have a perfect square that divides into it? You should say, oh yeah, we can put a 4 in there. So the 8 becomes the square root of 4 times the square root of 2, because 4 times 2 is 8. So no longer are we looking at that. Now we see the square root of 9, which is a 3, the square root of 4, which is a 2, and then our square root of 2 that we can't simplify anymore. What do I do with the 3 and the 2? If you say multiply, you are correct. And so the final answer here is 6 radical 2. Now, had you gone back to the 72 and, oh my goodness, 36 divides in there, then you would have gotten straight to the 6 radical 2 instead of having to go through this. All right, go have some fun.